be like the star. That would be like the stars. That's not like the planets. The planets don't spin like the stars.
Yeah,
They do. They make.
yeah. And then there's a boy on a merry-go-round here on near me, and when I spin, I see that the boy is not perfectly spinning around me, but is making a very strange flowery pattern around me. Because he's on the merry-go-round and I'm spinning on my axis, and what I see is the boy making a flowery pattern.
But
Try that.
you just said it would be the same in every planet in every solar system.
It would not be the
So
same. It
how is
depends what the
how
planets
is
are
that
doing.
boy? How is that boy always the same distance away? How is this
Because the
relatively
because the
gravitational?
merry-go-round is some distance from me. I'm spinning on my axis, so the merry-go-round plus the distance from the boy uh, to the center of the merry-go-round, they're fixed quantities and lengths and things like
Come
that.
on, bro. Like even you don't
Okay,
believe what you're saying right now. Like
I
come
believe
on.
what I'm
Like,
saying. I can assure you. I have my friends here who are smiling, very pleased
What
about
type
what
of credentials they got, Franco? They particle physicists, they astrophysicists, they nuclear physicists. What's your friends?
that's
they're particle. One of them is particle physicist. The other one is his wife.
Oh, ask them if virtual photons are a reality in
They
real
want to
life.
know if virtual photons are real. That's a
Hey,
good question.
hey, real quick, if I can
What
add
happened?
this in.
Hold on. I'm waiting for the answer. It's taking way too long for
I don't
this.
want to involve them. I don't want to involve them against their will, but
Yes or no? That's hard. Why is that such a hard question for
are
the particle
virtual.
physicist?
Here's the particle physicist. Are virtual photons real or not? Yes or no? This is a question because if look, if you answer wrongly, it means that the Earth is flat. Right. Right.
Straw man.
Virtual photons are an approximation of the perturbative theory of quantum field theory.
No, okay.
Does that so if the wait. So if they're in the perturbative theory, this means
You,
it's
that's the end of you. Right.
Okay, okay, but
that's a theoretical construct.
Yeah, I didn't get a yes or no answer.
No,
I didn't
that is
really.
it. That is a yes. That's a no. Actually, is because when you the perturbative theory is not. It's not. It's real. It's a mathematical thing.
It's
So
an
it's
abstract
100%.
concept.
Yeah, it's
Yeah.
100%. So he just verified that that's a no, essentially.
We learned about them expansions earlier today, Franco. Appreciate that.
So Franco, I have a question about the pendulum because that's why you came up. Um, so
also
Coco
with that
pendulum. Yeah.
pendulum. Wait.
Sorry. I'm dismissing my friends. Sorry, because I don't want to
Okay.
involve them.
Okay. Okay.
Yeah.
Um, yeah. So I wanted to know, how would you change it, right? So, for example, you have this equation, and let's say the equation is predicting things well, but then there's a change in the periodicity of the pendulum. How would you account for that to kind of keep the construct of it being the rotation of the Earth, right? Because they're saying that it's the rotation of the Earth that causes it to uh, do what it does. So when it comes to the periodicity changing, how do they correct for that? I'm just curious. If you don't know, that's cool. I'm just curious if you know.
I don't know. We would have to see what other factors are coming in. Depends. Every experiment is subject to a lot of possible systematic error sources, and you have to evaluate those and things like this. So it
Okay.
depends on the situation. I cannot.
So quick. So one more follow up. One more follow up. Last question. So let's think about this. If it's the Earth that's spinning that is causing the movement that we see when it does its little design on the floor, the pendulum, and then it changes at specific points in the year or specific events like eclipses. Is that do you still continue to believe that it's the spin of the Earth that's causing it, or do you change and question the fundamental assumption that it's the Earth spin and start to think that maybe it's something else? Because the Earth obviously didn't change its spin to change the periodicity or the precession of the pendulum, right?
Right, and yes, I would like to. When I see an experiment that does not confirm what the expectation is, I would just try to investigate what caused this discrepancy, and see if it's an experimental problem or if it's a problem of the prediction, or if there are some other effects coming in. I don't know. It depends.
Fair,
It
fair
depends
enough.
on the particular situation.
Fair enough. I respect it. Thank you.
Problem.
Okay. Let's address this straw man. Who specifically said that weather was impossible on a globe Earth?
Weather is impossible on the globe Earth.
Yeah, who said that?
I don't have no idea.
What you mean?
I don't know. I don't know all the quotations of every person in the world.
Well, wait, you went to the timeline, right? And then you said, I'm gonna think about what I want to say. This is the best thing to say. Hey, Piper, I heard them discussing how seasons are impossible on a globe last week. And they
Oh
claim
yeah,
they
yeah,
can
yeah.
discuss virtual
Sorry.
photon.
Yeah. Last week you were discussing the tilt and how the tilt is not compatible. The tilt on a globe is not compatible with seasons. That's really astounding to me. Not understanding this.
I'm gonna ask you. You said I heard them discussing how seasons are impossible on a globe. Who said that?
You said that it made no sense. That it made no sense on the Earth. The tilt explanation. I definitely heard that.
thought
I cannot quote you because I didn't record it. But people were saying this. It's not possible on. It's not possible. The tilt explanation is not viable. It's not working.
didn't we ask for a demonstration? Didn't we ask for reproducibility?
I don't know. I didn't hear that. I heard.
Of course. And this is what all right. You know what? I'm gonna chill. Go ahead, Franco. I just asked you a question. I'm gonna let you finish.
I heard you guys saying that the tilt was not explaining the seasons, and David Weiss saying that how come, he said something like, how come that in winter when I see the sun rising, the light from the sun is colder than it is in summer at the same time of day, meaning at sunrise. This is completely a nonsensical objection because it's not true. It's simply not true. You just measure the solar irradiance as a function of angle, and it does not depend on the season. What changes during the season is the temperature of the air around you, and that's why you're freezing on a winter morning, and you're not on a summer morning. But this has nothing to do with the inclination of the sun with respect to the zenith. Nothing to do with that.
That's interesting. That's interesting. I'm glad that you said that. When did you and Dave Weiss talk about virtual photons?
We didn't.
So when are you going to start telling the truth? You said I heard them discussing how seasons are impossible. So I said, who you was talking about? You finally said a name. Oh, David Weiss. Then you said, and they claim that they can discuss virtual photons. So you're referring to David Weiss about seasons. Then
No,
I
I'm
asked
talking
you,
about your group. I'm talking about your group as a whole. And what I'm saying and what I repeat here is that people are not in a position to discuss relativity and quantum field theory if they don't understand basic facts such as simple
it was just a question that was asked to you, and you didn't answer it. As a matter of fact, I just asked your friends, right? And they didn't answer my question either. So you saying I'm not in a position to discuss it, even though you
yes,
just brought up,
because maybe
even though you just brought up David Weiss, you said that I'm not in the position to discuss it. So then
yes,
when I get to asking you questions, just like your students ask you questions, for some
maybe
reason I don't get an answer. So for someone to sit there and say, hey, Sacred, you can't talk about this because you don't know as much as I do. Okay, hey, Franco, can you tell me about this? No, it doesn't matter. It doesn't matter. I don't have to tell you about how it works in reality. So on one hand, I can't talk about it because I don't know about it. Then when I ask you about it, you don't want to give me the answers. How can I avoid you running to the timeline talking shit about it if you're not giving me no way out? I just got to shut up around you. Is that what it is? I can't talk to you about it. I can't ask no questions about it. When I do ask questions, I don't get no answers. How do you handle your students? Every time your students ask you a question, you tell them get out the class. They can't talk about it. They don't got a PhD. I'm
My
confused, Franco.
students do not make questions like that. Do not ask questions like that. The fact
They
that my
should.
friend my friend who is a esteemed particle physicist, he did not answer he did answer the question the same way I did about virtual photons, means that the question you make has that answer. That is the way this question answered. A question like are virtual photons real does not make sense for a particle physicist. It's not the way we ask questions. And my answer to your questions is, if you want to learn physics, you start from the basics, and then when you have learned the basics very thoroughly, you can start to go to advanced physics step by step. And my students are doing exactly that. I teach basic physics for first year. I teach electromagnetism the second year. I'm teaching introduction to particle physics the third year. I'm teaching experimental physics to PhD students after they have gone through this step-by-step procedure, and they do not ask questions like that.
So they don't ask questions about reality.
No.
Y'all hear this?
You can laugh,
Y'all
but
hear this?
that's the way science works.
All right, that's cool. Y'all don't talk about. Y'all don't ask questions about observable reality. And y'all talk about physics.
Yes,
It's about testing observable reality.
I have a whole, I have my whole course for PhD students this year was about observables, was about what we call observables in particle physics in standard model. So yes, it was about that. And just to give just to give a final answer, I've thought up an answer to the reality question about virtual photons. I'd like to put it like this.
After you calm down from Rage Queen earlier, I'm glad that you did think about it.
Yes, yes, because again, this is not the way things are done normally. You must have time to think about an answer, right? Especially again, if you're on spaces like this, because this is not a normal place when discussions in science take place. Again, about reality of virtual photons. I even posted a paper, and I posted some pictures. What is real, what is considered real in a way, again, it's not in an ontological, it's not in a philosophical way. What is considered to be real is the electromagnetic field. The electromagnetic field has some consequences. When you want to compute the consequences of the interaction of this particle with an electron, say, or the way the electromagnetic interaction produces, say, scattering between charged particles, you need to compute the probability, what is called the cross-section, for such an event. And in order to compute this, you have to follow a certain procedure which involves the so-called Lagrangian of the model, or the Hamiltonian of the model, which tells you what are the rules for using this form of the interaction that you've postulated. And as as I was saying yesterday, this calculation is not computable analytically, meaning that there's no formula for it that you can come up with. And what you can do, as my friend just said, is a perturbation expansion with terms at various orders of this expansion. And each term contains various an increasing number of terms, which involve the so-called Feynman diagrams, which involve the so-called virtual photons, which are not real in the sense that, for instance, to compute the fourth order for-loop contribution, for instance, to the anomalous magnetic moment of the electron, you need to compute an enormous number of these Feynman diagrams, each with a different exchange of the virtual photons, and you have to sum up all these terms, which are complex numbers, and then take the modular square of that sum, which means that they cannot be considered real processes, real exchanges happening, because you're summing them up. To describe the same physical problem, the very same physical process, you are summing up an enormous number of different virtual photon exchanges, which are indeed actually only terms in a approximate calculation.
Right, because
They're not real. What is real is the field. The virtual photons appear in the way you compute the effect of the field on electrons, for instance.
But the last time we asked you what a field was, you couldn't even really define it for real. I think you said it was just like another mathematical calculation. But aside from that, you wouldn't need, just like D3 said, you wouldn't need any perturbation if the actual calculation initially worked. The only time you implement that.
Would you be satisfied if I told you that a field is an operator in a Fock space or in an infinite Hilbert space? Would you be satisfied with that? You have to learn all the mathematics with it, and then it's perfectly defined.
Yeah, of course you got to learn the mathematics, but that doesn't mean that it's an explanation, right? It's not. All you're doing is describing something mathematically, but that you're getting away from my point. My point is you needed to incorporate the perturbation, and just like D3 said, you wouldn't need that if your calculations was initially correct. It literally
no. It's the same as. Okay, another example. Suppose you want to this I thought of this morning. Suppose you want to compute the area, the surface area of your room, of the room you're in. How do you do that? How do you measure the surface area of the room you're in, of the floor? How do you measure that?
Each surface.
Sorry.
Each surface.
Just
the floor. Just the floor.
Yeah, just the floor.
I mean, if it's a perfect square, length times width.
Is it a perfect square?
It depends on what it is.
Yeah. Suppose it's a room you're in at the moment. How do you have to give out the value of the surface area of the floor? How do you do that?
It depends on how precise you want it.
Yeah, precisely. It depends on how precise you want it. And
right.
if you want to go to measuring the length at the micron level, you will find that it's not a perfect rectangle. And if you want to go even down to 10 to the minus, I don't know, to the fraction of a micron, you will see that the borders are not straight. And then you would have to compute it to a certain degrees of approximation, and also you have to take into account the precision of the measurements of the measurement instruments you're going. So it's everything. Every single measurement and every single quantity in physics is never exact. It's always an approximation to some degree. So that's also true for calculations.
Yeah, but this is not a general instance. We're talking about something.
It's a general instance in physics. It's a general instance in physics. You always compute things to a certain degrees of approximation, and you compare them to reality to a certain degree of precision, and that's the basics of experimental physics.
So what would be the problem before implementing the perturbation theory? Like, what would be the actual problem?
Hey, real quick, I want to say I think that was Witz who was challenging the original presumption. The math, for me, I willingly admit that this shit is over my head. But go ahead and answer Sacred's question.
The problem, the problem that Witsit was referring to is the anomalous magnetic moment of the electron, which is measured to be something different from the G value that is equal to 2 in Dirac's simple theory. But that means that the theory was not applied to all degrees of correctness. It's the thing that Witsit says is a misinterpretation of what actually happened. It's not like we introduced something new was introduced to explain an anomaly. It was a calculation done in a better way, and finally using the same thing, which is the electromagnetic field, not introducing anything else, but improving the way of making calculations with this perturbation theory. Then you have an incredibly successful prediction of what this number should be, and agrees and with the
Hey, let me ask you a couple questions.
That's after it fails and you correct for it. But go ahead, D3.
No, it's not after it fails. It's just that you measure something, and it's not in a theory that was being developed. Because Dirac's theory is from the 30s, by the way, with enormous success because it predicted the anti-electron. It was discovered 3 years after the prediction, and things like that. And then things were still developing. Quantum mechanics was very young. It was developed in the 20s, and then in the 30s, Dirac went on with his theory of fermions, and then in the 40s and the end of the 40s, the quantum field theory was developed. So it was very quick. It was very quick.
Last question before I pass it off to D3. Can you just explain what is the difference between the implementation of a virtual photon relative to the implementation of dark matter and dark energy? Because that was like the main, like, blatant layman's term.
No,
like
nothing to do with each other.
I didn't say that. I didn't say that had anything to do with each other. What I'm saying is, if they're both abstract concepts. And Witsit was saying, well, what's the difference? What's the difference between us saying, hey, relativity works, until we actually started looking for the components of what they needed for relativity, found out that we were lacking some of the components, so we had to implement some abstract concepts of dark energy and dark matter and a bunch of other things that's wrong with the expansion of the universe. So he said, what is the difference between that and what y'all did with virtual photons?
It's totally different, because virtual photons is a way of making a calculation of something that has been postulated, which is the electromagnetic interaction, and done which has some form in quantum field theory, right? And this is just a way of making calculations using virtual photons. It's nothing to do with dark matter, which is something which has been introduced to explain the observed rotational curves in galaxies, in spiral galaxies. It was not born with the coma cluster problem that Witsit was referring to yesterday. It's not that. It was I learned about dark matter first time when I was a student, and it was introduced to me in the astrophysics course that I followed with the problem of galactic rotational curves, meaning the velocity of stars as a function of radii from the galactic center, which does not follow the same shape as predicted if the mass distribution follows the light distribution, if it's proportional. So it means that
don't they need dark matter for that same calculation?
They need dark matter. They introduced dark matter to explain, because it was an observation of an explanation of the observation of velocities in galaxies, and then of velocities of galaxies, which did not follow the prediction from
based on calculation, right?
Based on calculations, yeah, and then so something here is missing, something like some mass which is not visible.
Not just some. It's like 60%.
No, it's not 60%.
Ain't it like 60% dark matter and like 30% dark energy or something like that?
It's no, it's something different. The percentages are different. But now dark matter is something that I'm not a cosmologist, but it's something that is really, there's really no doubt about, because it also explains the large-scale structure of the universe. It also explains the so-called cosmic web, which is the way actually galaxies are arranged in the cosmos, which is not uniform, but it's
Just real quick. This come from Harvard.edu. The universe is mostly dark. About 96% consists of dark energy, which is about 69%, and dark matter about 26%. So I had them reverse. So the dark matter is about 30%, and the dark energy is about 70%, which accounts for about 96% of our observed universe.
Yeah, but dark in the two cases does not mean the same thing. But anyway, okay, it was an unfortunate.
That's where the accelerative expansion of the universe. They need to explain that, so they had to put energy there. But all I'm saying is they had calculations put in place, and then they made observations, and they were missing stuff, so they had to implement things to make the calculations work.
Yeah, that's
so
what.
So when you're saying like the virtual photons is all about calculations, and this isn't, but then we say, well, we needed these for the calculations. Again, I'm back to square one. What is the difference between the two? I'm not saying that they're related. I'm just saying, what is the difference of the process of implementing them? What's different between implementing a virtual photon to explain an observation versus implementing dark energy and dark matter to explain an observation that failed? What's the difference?
I'm trying to explain. Virtual photons is not something new that has been introduced. It's not a new agent. It's not a new concept. It's not a new particle. It's something that allows you to make calculations. It's a way of making a calculation. It's that. It's the way you have to put together the various terms in containing the electron field and the electromagnetic field in various terms in a serious expansion of your calculation. Just a mathematical way of doing this calculation. So it's something new, which was unexpected, and which was introduced. Dark matter.
You're talking about virtual photons?
Yeah, the virtual photons.
Okay.
And virtual in general. Yeah. And they're not something new introduced, right? Like, for instance, the top quark, yes, it was something new introduced, or the charm quark was something new introduced because that is something like that can be sort of akin to the dark matter, because the charm hypothesis was introduced in the 60s. The charm quark hypothesis, because of was explaining mathematically in a very, very beautiful way the fact that some process was predicted but not observed, meaning flavor changing neutral currents. They were predicted, were not observed, and so Majani, Glashow, and Heliopoulos came up with this hypothesis. What if there are 4 quarks instead of 3, and the fourth one we call it charm because we have imagination, and that this charm quark should be, by its virtual effect on measured processes that we have seen so far, it would act so that it would cancel out some of these diagrams, and so it would make this process, which we don't observe, suppressed, we say it. So it's not its probability is very, very, it's not zero, but very, and then in 63 no 73 or 74, the J-psi meson was discovered in America. It got the Nobel Prize. It was discovered in the same days in 2 laboratories in America, and it was discovered after it was predicted due to the predicted virtual effect. So this is something which is something new, which wasn't part of the model at that point, the 4th quark, and then it was introduced and it was discovered. Same for the top quark, which at this point everybody believed it was there, but it was discovered in 1995 after, as I was showing yesterday with my plot, it was the mass was basically determined through its indirect effect by a virtual virtual top exchange in Feynman diagrams. So yes, it's sort of very vaguely akin to dark matter, because it's something new which wasn't in the model until up until a point, and then it was introduced to explain observations. Dark matter is something different, because it's not a technical way of doing calculations such as virtual particles are. It's something that it comes from observation. The measured velocities are not compatible with the hypothesis that the mass of a galaxy it's got the same distribution as the light. So it means that there is some mass which is not in stars. It could be dust. That was the first hypothesis. It could be just matter that we don't see because it doesn't shine, and that's why it was called dark. But then more observations found that it's not compatible with being gas, with being dust or whatever. It's not compatible. It's not even compatible with being the kind of matter we know about. It's not baryons for cosmological reasons. It's not electrons. It's not charged. Of course, it must be neutral. It's not, but it's not baryons for other cosmological reasons. It could be neutrinos. It's not the known type of neutrinos. It could be a new kind of neutrinos, but it could be some other particles we don't know yet. But it's observed because of the motion. And yes, some authors have proposed that what should be changed is the law of gravitation, and they have proposed various solutions, and none of them is accepted because it doesn't fit the data. That's why it's not like it's taboo to propose that the explanation is that the gravitation law is different. There's been a huge number of proposals in that sense. I'm not expert on this again, so I cannot quote them, but I know for certain that.
Before we get into like the new proposals and everything that they're trying to implement because all this doesn't work, I'm just trying to figure out the difference. And now it seems like you're saying it's because of the time frame, because one is new and one is old.